So I'm going to follow Steve Ward's lead this morning and take the chair's opportunity to take precedent and just start off with one question to Rob Dunn to start with, but also to ask Alan Fairland and Julio Mata in the audience as well, because they're both involved in drug discovery and development for Leishmaniasis. All the drugs, the new treatments and drugs we've got are based upon repurposing those that are already there. Is the absence of novel treatments or novel drugs for Leishmaniasis due to the fact it's really just a very difficult parasite, or is it due to lack of resource and focus to able to focus on getting a new drug through into clinic?
I think, and dare I say it even a little jealously, compared to some of the other diseases like malaria, Plasmodium, the hit rate in the screens is extremely low, and we tend to keep coming up with the same scaffolds. It really, there is very, very little chemical diversity and chemical matter that hits the parasite in the screens that we have, which are the ones we're using, is the intracellular form. And as I said, the compound, which at that point is not optimized as a drug or a drug candidate, has to have quite significant drug-like properties just to hit the parasite. And there are approaches even of screening Axenicae mastigotes, and we have some healthy debate about that at times. We have the extracellular form, but there most of those hits don't cross over without optimization to hit the intracellular form. And how much do you want to invest on something which you're not quite sure is going to have the same target, or the target will be active in the intracellular? So it's really hit rate in me, but to the two of you.
Two gentlemen both sitting on the same row. If you could get the microphone.
Yeah, I think that I'm a newcomer in parasitology, so I'm looking for on the outside. I wouldn't say that it's a fascinating biology, so it's difficult, it's complex. Trying to translate this into a microtiter plate on a well, that's really a challenge. But I think it is not more challenging than many other areas. I think in all therapeutic areas for the pharma industry. I think the challenge here has been the lack of resources, for sure, and systematic approach. We lack a standardization of assays and models, so it's very difficult to compare back-to-back activities. Compounds coming from one organization that are handed over to another organization, and maybe they fail in the first run because the lack of standardization. So I think it's lack of resources, in addition to the biological challenge. But I think it's also, that's related with in vitro, but I think it's also the lack of information and knowledge about how to translate this, not only in animal models, but it's translational biology and translational medicine. I mean, there is very little information about clinical trials that you can take back to animal models. So there's a tremendous debate still between mice and hamster. What's the most relevant? You cannot optimize a PK in hamster, which is not related with human, because the disease seems to be more clinically relevant in hamster. I mean, this for us, that we are trying to develop and optimize leads, is some misleading or confusing, might be. So I think it's clinical trials that are properly designed with clear readouts, biomarkers that could feed back the early discovery. I think is also a tremendous gap in this disease.
I agree with all the comments that have been made by my illustrious colleagues, and there's very little to add to that. Really, there's a basic lack of the fundamental pathobiology driving these things, and this issue of why molecules do not operate once within the macrophage is a very interesting and challenging area to be looked at. And as Professor Croft knows only too well, a macrophage is not just a single macrophage type. There are many different types, so there are layers of complexity added on there. We are exploring new areas of chemical space in the drug discovery unit in Dundee. We're moving outside of pharma space. We're not. I don't think anybody is seriously engaging in natural product drug discovery, which I think is always an underrepresented area of research. And at the risk of offending my medicinal chemistry colleagues, of course, they are highly immunized against molecules that may operate via reactive mechanisms. So, for example, fexinidazole, which is now under development both for HAT and being evaluated in a combination, I believe now, for visceral leishmaniasis. That is a molecule that, all young, upcoming medicinal chemists have been completely immunized against. And the same would apply to VL2098 and the equivalent nitro compounds under development for TB. So there may be a lesson learned there, but there are issues that you have to bring to the fore. If you decide to take that kind of strategy, you need to be on the lookout for immune reactions and, of course, carcinogenicity and immunogenicity. So I don't think there's a simple way to discover new drugs. If it was that easy, pharma would have upped their productivity enormously over the past 50 years. It's essentially remained static. So academics should not get too arrogant and think that they know all the answers. We don't. It's a hard slog, but I don't think it's any more difficult with leishmaniasis than any other neglected disease.
Steve Ward, just behind you.
Just following on for those comments, I mean, most pharma libraries are driven by structures which will hit kinases and G-coupled proteins, etc., etc. They haven't been designed to try and penetrate a cell and then to try and penetrate a partially acidified a suborganelle. So has anybody systematically, just using chemistry, established the Lipinski-type rules for penetration into a macrophage compartment where Leishmania is replicating, and then applied those rules to the chemistry that they drive in their screens?
So my reply to that, Steve, you also work on TB, and so did the group at Dundee. TB, mycobacterium, lives in exactly the same compartment. Has it actually been applied to antimycobacterial drugs?
We are, and the rules are very different.
So that could be a lesson then?
I think to say that the hit rate in the screens is poor, which is a fact, realise the fact that the molecules that you tested haven't been designed to work necessarily in that environment.
Just to comment that Lipinski rules are for oral drugs. So making compatible penetration into the macrophage, the phagolysosome, with oral drugs maybe it's even more cumbersome. So it's just to bear in mind. So if we want to have make an oral drug, maybe we have to follow Lipinski rules, is when this is applicable to. If we want to find another formulations, or maybe we need to design new formulations for this new chemical matter.
My argument is that we should abandon the Lipinski guidelines of rules when we're talking about pathogens in general, and certainly when we're talking about intracellular pathogens.
Yeah, well, of course, I mean, Lipinski at the outset, when he developed these rules, he eliminated all natural products. And so we have amphotericin B and paromomycin as examples of natural products. So Lipinski's rules de facto do not apply.
Just a quick comment on that. And I think once we understand a little more about some of the targets, we can start using the hits in Xenico mastigotes that don't work in the intracellular form to start to dissect some of that. In fact, I was just talking to Jean-Aubert, who was asking if we might be able to make that some sort of open source research project in the coming years. So maybe we can talk about that this afternoon.
So, linking to that and thinking about the work that the malaria and TB people have had to get through, which is about predictive models, and it was alluded to by you, Rob, and also by Alan up there, that maybe we don't even have the right models then to take something through, and hamsters were vaguely mentioned up there by Julio as well. We don't have the right models, and the people who work on Plasmodium haven't had right models for years because there is, well, Plasmodium berghii isn't the same as Plasmodium falciparum, and yet they've managed to get compounds through. Are we reliant on the wrong models which are leading us astray?
Personally, we're in. Oh, Wes, yeah.
You want to answer first?
No. Okay.
From the MMV standpoint, the big breakthrough, I think, has been to stay in animals as short as possible and go right to humans. And that's been the big breakthrough, I think, that's led to the pipeline of 10 or 12 drugs that are now in human trials and so on. So I think that's the take-home, is that no model really was good.
Yeah, I was about to say much the same. I think the best model is the patient. I think we need the safety, obviously, before we go there. And we can start to work back from that as we take a few through clinic. But we do face a higher risk of failure because we don't have a good validation into the human.
And also running the clinical trials as experimental medicine, as a way of eliminating or dropping agents. Right. So maybe we have to encourage the regulatory agencies to accept designs which is about learning, not about dropping, falling drugs.
Any other comment from anybody in the audience on those particular points before I try and include Albert in a question? Okay, Thomas, sorry, Thomas.
You mentioned a lot about phenotypic screen for leash. Can you comment a bit more on the target-based approach?
At the moment, we don't have good validated targets. And when we first started, we really started to look at some of the targets and well, it's a catch-22 where, in a sense, from D&DI's perspective, it's difficult for me because it means going further back the pipeline, which is harder for me to justify internally. And what I want to do, and I think perhaps Wes will talk more about this later on today, is to make a greater resource out there for other people to identify targets that ultimately we'll probably have to look at.
Okay, so obviously mentioning facilities and resource and funding, etc., for this area. Obviously, one of the key resources that you always need is the trained expertise in called human beings, I think they're called. Apart from Babsi, mice and humans sort of rank equally, I think, in this sometimes. I mean, Albert, just coming to you, I mean, obviously, I know you put a huge amount of effort into getting this PhD program off the ground, but should you already be thinking about the next steps, which to choose or to give the opportunity for some of those PhDs, say 4 postdoctoral fellowships, 2 in industry and 2 in academia to follow on, because this is about career structure, not just getting a PhD if we want to make long-term damage to these diseases.
Well, I think that's a very good point. I mean, that's one of the problems that we're facing. We, at least at these schemes at the European level, they are really structured. You can be trained as a PhD and then you need to apply for another training as a postdoc. We will need definitely like a long-term training program, not just for Leishmaniasis, but as a general program, to ensure that people that are trained at the PhD level then can join the industry or join the non-academic institutions and follow on. We, as far as we have here, is just with inverted commas if you want, PhD program, but hopefully we will be working with the fellows to ensure that they have the capacity and the interest to keep working on research, to keep working on Leishmaniasis, and hopefully to as well keep working with the non-academic institutions after the program.
Should we be lobbying the people in Brussels to make sure this happens?
Always, we need to lobby always.
Okay, Cameron, I think I've just been given the time is up, so thank everybody very much for their contribution.
Thank you.